The Republic F-105 Thunderchief stands as one of the largest single-seat fighters ever built, weighing an astounding 50,000 pounds fully loaded. This massive aircraft could reach speeds over Mach 2 and carry a bomb load greater than a World War II B-17 bomber. The F-105 Thunderchief represented a significant leap in aircraft engineering during the 1950s. Each variant, from the initial F-105 Billion to the specialized F-105G Wild Weasel, showcased remarkable technical innovations. The Thunderchief's development pushed the boundaries of aerodynamics, material science, and weapons integration, creating an aircraft that served as both a supersonic fighter and a powerful strike platform. This video will examine the extraordinary engineering achievements that made the F-105 possible, from its revolutionary design features to its advanced electronics and structural innovations. You will discover how engineers overcame significant technical challenges to create this remarkable aircraft. Revolutionary design features. The F-105 Thunderchief incorporated several groundbreaking design features that set new standards in military aviation engineering. These innovations address specific challenges in supersonic flight, engine performance, and weapons delivery capabilities. The F-105's distinctive silhouette emerged from the application of the area rule concept, a breakthrough in aerodynamic design. This principle led to the aircraft's characteristic wasp-waisted fuselage configuration, which significantly improved transonic performance. The implementation involved careful contouring of the fuselage to compensate for the wing's cross-sectional area, resulting in what engineers dubbed the Coke bottle shape. This design innovation delivered remarkable results, with tests showing a 60% reduction in drag rise near the speed of sound. The benefits of implementing the area rule were profound. The design fostered smoother airflow transitions across the airframe, minimizing turbulence and drag. This reduction in transonic drag not only improved the aircraft's overall high-speed performance but also enhanced its fuel efficiency during supersonic flight. By effectively leveraging the area rule, the F-105 emerged as a marvel of aerodynamic ingenuity, setting a new standard for fighter-bomber capabilities in the supersonic era. The F-105's air intake design represented a significant departure from conventional approaches. The aircraft featured unique reverse swept air intakes positioned at the wing roots, leaving the nose free for radar equipment. This configuration served multiple purposes, primarily reducing the likelihood of engine stall caused by high-speed shock waves in the engine inlets. The intake geometry included an adjustable ramp inside the duct, allowing for optimization across various flight conditions. The internal weapons bay exemplified the F-105's versatile design philosophy. Originally configured to accommodate nuclear weapons, such as the Mark 28 or Mark 43, the bay measured 15 feet 10 inches by 32 inches by 32 inches. As mission requirements evolved, engineers adapted the space to house a 1,476-liter auxiliary fuel tank, enhancing the aircraft's range and operational flexibility. The weapons bay design complemented the aircraft's impressive fuel capacity, with 4,396 liters distributed across 7 fuselage tanks. This integration of fuel and weapons storage capabilities made the F-105 particularly effective in its intended role as a low-level interdiction aircraft. Powerplant Engineering. At the heart of the F-105 Thunderchief's impressive performance lay its powerful propulsion system, which represented a significant advancement in jet and technology of its era. The F-105 Thunderchief's power plant centered around the Pratt & Whitney J75 PW an impressive 24,500 pounds of thrust in standard configuration. With the afterburner engaged, the engine's output increased to 26,500 pounds of thrust. The integration of the J75 P19 Debbie engine into the F-105's design was marked by several advanced features that maximized its potential. Among the most critical was the inclusion of a water methanol injection system, which provided a significant boost in performance during demanding missions by cooling the engine and increasing thrust output. Additionally, the variable geometry air intake system was a key innovation, allowing the engine to adapt to varying flight conditions by optimizing airflow for both subsonic and supersonic speeds. The aircraft's airframe was specially reinforced to handle the immense power generated by the engine, ensuring structural integrity even under the stress of high-speed maneuvers and demanding combat operations. This strengthened design also enhanced the Thunderchief's ability to absorb and withstand battle damage, bolstering its survivability in hostile environments. These features combined to make the F-105 a cutting-edge machine of its era, showcasing a seamless integration of advanced propulsion technology and rugged engineering to meet the challenging demands of supersonic warfare. The J-75 engine utilized an advanced four-stage afterburner system that provided exceptional thrust augmentation. This sophisticated setup allowed pilots to maintain high-speed performance even under demanding combat conditions. The engine proved remarkably resilient, with former pilots noting its ability to sustain operation even after taking significant combat damage. The afterburner system featured distinctive flower petal speed brake doors that extended in pairs when deceleration was needed. This dual-purpose design exemplified the engineering team's focus on functional integration, allowing for both thrust enhancement and aerodynamic control. Initial operations revealed cooling challenges that engineers addressed through several modifications. A notable solution involved the installation of ram air intake scoops on the rear fuselage, specifically designed to resolve afterburner cooling issues that had previously resulted in engine fires. The cooling system underwent continuous refinement to enhance reliability in various operating conditions. Engineers implemented several key improvements. The hydraulic system initially showed vulnerability to battle damage, prompting modifications that significantly improved the aircraft's combat survivability. These upgrades proved crucial during extended combat operations, particularly in high-temperature and high-humidity environments where electronic systems faced reliability challenges. The integration of these cooling improvements with the basic engine design created a powerplant system capable of sustained high-performance operation. This engineering achievement enabled the F-105 to maintain its remarkable speed capabilities, including the ability to operate effectively at both high altitudes and in demanding low-level flight conditions. Aerodynamic breakthroughs. Advanced aerodynamic engineering defined the F-105 Thunderchief's remarkable performance envelope, setting new standards for tactical aircraft design in the 1950s. The F-105 Thunderchief's wing design was a cornerstone of its advanced aerodynamics and versatility, showcasing a careful balance between speed and stability. The wings were crafted with a pronounced 45-degree sweep angle, a configuration deliberately optimized to enhance performance at high speeds while maintaining reliable stability during low-altitude flight. This sharp sweep angle allowed the aircraft to minimize drag at transonic and supersonic speeds, enabling it to perform effectively in missions that demanded rapid transit and agility in hostile airspace. The mid-wing monoplane layout further reinforced the aircraft's aerodynamic efficiency. By positioning the wings midway along the fuselage, engineers ensured a balanced distribution of lift and weight, contributing to the Thunderchief's remarkable stability across its entire operational speed range. This design choice also enhanced control responsiveness, making the aircraft adept at handling the dynamic challenges of both high-speed flight and low-level navigation. Another defining characteristic of the F-105's wings was their high loading, which brought significant benefits to the aircraft's performance. This design feature enabled the Thunderchief to maintain excellent handling at high speeds, ensuring precise maneuverability even in demanding combat scenarios. Furthermore, the stability provided by the high wing loading was especially advantageous during low-level operations, where the aircraft needed to fly at high speeds while avoiding ground-based threats. The wings also contributed to a smoother ride in turbulent conditions, an essential attribute for maintaining pilot effectiveness during long and challenging missions. By combining advanced aerodynamic principles with practical design elements, the F-105's wings exemplified the fusion of cutting-edge engineering and combat functionality, establishing the Thunderchief as a formidable asset in supersonic flight and strike operations. F-105 Thunderchief achieved impressive speed capabilities, reaching Mach 2.08 at 36,000 feet. This remarkable performance stemmed from the careful integration of the swept wing design with the area-ruled fuselage. The aircraft demonstrated extraordinary climbing ability, achieving a rate of 38,500 feet per minute, enabling rapid transitions between altitude levels during combat operations. Perhaps most impressive was the F-105's low-altitude capabilities, where it truly excelled as a tactical fighter bomber. The aircraft could maintain supersonic speeds at sea level, a crucial advantage when evading enemy fighters. During combat operations in Vietnam, pilots pushed the F-105 to its limits, reaching speeds up to 870 knots at extremely low altitudes. The Thunderchief's aerodynamic prowess proved particularly effective against contemporary fighters. Despite its substantial size, the F-105 secured 27.5 confirmed air-to-air victories against enemy aircraft. This success stemmed from its ability to use pure speed as a defensive advantage, particularly against Mach 17s and Mach 21s. The aircraft's design prioritized stability during weapons delivery missions, with the high wing loading providing a steady platform even in turbulent conditions. Landing operations typically occurred at speeds around 230 mph, demonstrating the aircraft's demanding yet manageable flight characteristics. Combat experience validated the F-105's aerodynamic design philosophy. The aircraft's ability to maintain high speeds at low altitudes proved invaluable during strike missions, particularly when penetrating heavily defended airspace. The combination of swept wings, a powerful engine, and an optimized airframe enabled the F-105 to carry substantial weapon loads while maintaining its performance envelope, making it an effective strike platform throughout its operational life. Advanced electronics. Electronic systems formed the technological backbone of the F-105 Thunderchief, marking a significant shift toward integrated avionics in military aircraft. The aircraft's sophisticated electronic suite enabled precision strike capabilities in all weather conditions. The F-105's fire control systems evolved significantly throughout its service life. The initial F-105 billion utilized the Mach 8 fire control system with an AP-31 ranging radar and K-19 gun sight, enabling nuclear weapon delivery through toss bombing capabilities. A major advancement came with the F-105D's and ASC-19 Thunderstick system, which provided superior targeting accuracy and expanded the aircraft's all-weather strike capabilities. K-system improvements included integration with R-14 radar for enhanced targeting, advanced bomb-toss computer systems, missile launch computation capabilities, and automated weapons delivery features. The F-105D incorporated sophisticated navigation systems that significantly enhanced its operational capabilities. The aircraft featured the AP-131 Doppler navigation radar, working in conjunction with the FEIC-5 automatic flight control system. In 1969, engineers upgraded 30 F-105Ds with an R-92 LORAN equipment for enhanced navigation precision. The NASA R-14 radar system was a groundbreaking technological advancement that significantly enhanced the operational versatility of the F-105D Thunderchief. This sophisticated radar system was designed with multi-mode capabilities, enabling the aircraft to excel in a wide range of missions and setting it apart from earlier models. Its advanced features expanded the Thunderchief's effectiveness in both combat and navigational roles, making it a truly multifaceted platform. One of the radar's standout functions was its air-to-air target tracking capability. This feature allowed the F-105D to identify and lock onto airborne threats with precision, providing critical situational awareness and enabling the pilot to engage enemy aircraft effectively. Additionally, the radar's air-to-ground targeting mode was equally impressive, delivering pinpoint accuracy for strike missions. This capability proved invaluable in missions requiring precise delivery of ordnance, especially against heavily defended or time-sensitive targets. The NASA R-14 also incorporated terrain following functionality, a crucial feature for low-level operations. By enabling the radar to map the terrain in real time, the system allowed the F-105D to fly safely at very low altitudes, evading enemy radar detection and surface-to-air threats. This capability was particularly important for penetrating hostile airspace and conducting surprise attacks. Another key advantage of the R-14 was its all-weather operational capability. Unlike earlier systems that were limited by adverse weather conditions, this radar allowed the F-105D to perform its missions effectively regardless of visibility. Whether navigating through storms or engaging targets obscured by clouds, the system ensured that the aircraft remained operational in a variety of challenging environments. The system underwent continuous improvement, with later variants receiving solid-state circuitry upgrades for the R-14 radar, which was subsequently redesignated as R-14000. The Warner Robins Air Logistics Center played a crucial role in maintaining and developing these advanced electronic systems. Special variants like the F-105G incorporated additional electronic warfare capabilities. These modifications included sophisticated radar homing and warning systems, enabling crews to detect and counter enemy radar installations effectively. The Wild Weasel variants featured specialized equipment, including the Vector RWR, EAR 133 RAWs, and RAW 300 LWR systems. The integration of these electronic systems made the F-105 one of the first aircraft designed as a complete weapons system platform. This comprehensive electronic suite enabled precise navigation, accurate weapons delivery, and enhanced survivability in hostile environments, setting new standards for tactical aircraft capabilities. Structural engineering. The structural engineering of the F-105 Thunderchief exemplified the advanced materials science and combat-focused design principles of the 1950s. The aircraft's robust construction incorporated cutting-edge materials and innovative damage-resistant features that proved crucial in combat operations. The structural design of the F-105 Thunderchief represented a remarkable achievement in materials engineering, with extensive use of advanced titanium, alloys, and high-temperature polymer matrix composites. These materials were chosen as a cutting-edge replacement for conventional construction materials, offering a host of benefits that elevated the aircraft's performance and operational capabilities. By incorporating these innovative composites, the designers achieved weight savings of up to 40% compared to traditional titanium structures, a reduction that had profound implications for the aircraft's overall functionality. The significant decrease in structural weight allowed the F-105 to achieve enhanced fuel efficiency, an essential factor for extending its range and endurance during demanding missions. This efficiency meant that the Thunderchief could carry out operations over greater distances or for longer durations without compromising its combat effectiveness. In addition, the weight reduction contributed to an increase in payload capacity, enabling the aircraft to carry heavier or more extensive ordnance loads, further solidifying its role as a highly capable strike platform. Another key benefit of using advanced titanium alloys and PMCs was the improvement in the aircraft's service life expectancy. These materials provided exceptional resistance to environmental stresses, such as heat and corrosion, which are especially prevalent in high-speed, high-altitude operations. This durability translated into reduced maintenance requirements and longer operational periods between overhauls, ensuring that the F-105 could remain mission-ready under demanding conditions. The Thunderchief also benefited from superior fatigue resistance, a critical attribute for an aircraft subjected to the intense stresses of supersonic flight and low-level bombing runs. The robust structural materials allowed the F-105 to endure repeated high-stress maneuvers without compromising safety or performance, ensuring reliability even in the most challenging combat scenarios. Incorporating these advanced materials into the F-105's design was a forward-thinking decision that underscored the aircraft's advanced engineering. By leveraging the properties of titanium alloys and PMCs, the Thunderchief achieved a combination of efficiency, durability, and capability that set it apart as a premier example of mid-20th century aerospace innovation. Engineers developed an innovative approach to managing structural loads across the airframe. Initially, The F-105's hydraulic system showed vulnerability to combat damage, leading to a critical redesign. The solution involved adding a third hydraulic line along the aircraft's spine, separated from the dual flight control lines that originally ran together above the bomb bay. This modification significantly improved the aircraft's ability to withstand battle damage and maintain control even when hit. In parallel with this hydraulic system improvement, engineers also refined the stress distribution across the airframe to enhance overall structural integrity. Control surfaces were designed with redundancy in mind, ensuring that the loss of any single surface would not compromise the aircraft's aerodynamic stability. The wing attachment points were reinforced to endure the immense forces generated during high-speed flight and combat maneuvers. Load-bearing structures were distributed throughout the airframe to prevent the concentration of stress in specific areas, thereby reducing the risk of localized failures. High-stress regions received additional reinforcement to sustain the demands of supersonic speeds and low-altitude operations. These advancements in hydraulic system design and structural engineering significantly increased the F-105's durability and survivability. By addressing key vulnerabilities and incorporating robust features, engineers ensured that the Thunderchief could endure the intense demands of aerial combat, remaining a reliable and effective asset for its missions. The F-105 Thunderchief demonstrated remarkable durability in combat conditions. One notable incident showcased this resilience when an F-105 sustained a 1.2-meter wide hole in its wing from enemy fire, yet successfully returned to base. Lessons learned from combat operations prompted several critical enhancements to improve the Thunderchief's survivability. Engineers added armor plating to protect vulnerable areas of the airframe, ensuring greater resistance to enemy fire. Backup flight control systems were incorporated to provide redundancy and maintain control, even when primary systems were compromised. Critical structural components were reinforced to better withstand the stresses of battle, and vital systems received additional protective measures to safeguard their functionality under fire. The aircraft's structural integrity benefited from continuous improvement programs. Engineers implemented multiple modifications to address combat-identified vulnerabilities, including strengthened airframe components and improved protection for critical systems. These enhancements proved particularly valuable during operations in Southeast Asia, where the F-105 faced intense anti-aircraft fire and challenging combat conditions. The structural engineering of the F-105 represented a careful balance between strength and weight. Its titanium construction provided exceptional strength-to-weight characteristics, comparable to steel, while being 45% lighter. This engineering achievement enabled the aircraft to carry substantial weapon loads while maintaining its high-speed performance envelope. Combat experience validated these design choices, with the F-105 consistently demonstrating its ability to absorb significant battle damage and return safely. The aircraft's structural resilience became legendary among pilots, who often returned their damaged aircraft despite sustaining hits that would have downed other aircraft of the era. Weapons integration. The weapons integration capabilities of the F-105 Thunderchief showcased remarkable engineering versatility, transforming from a dedicated nuclear delivery platform to a multi-role combat aircraft. The F-105's design originally centered on nuclear weapon delivery, with an internal weapons bay specifically engineered for nuclear stores. However, engineers adapted the platform for conventional warfare through innovative modifications. The sealed internal weapons bay received additional fuel tanks, while external mounting points expanded the aircraft's mission flexibility. The aircraft's arsenal included M61, a 1 Gatling Type 20mm cannon for air-to-air combat, AG-12 bullpup air-to-surface missiles, AIM-9 Sidewinder air-to-air missiles, 2.75-inch rocket pods, napalm canisters, conventional bombs of various sizes. The F-105 demonstrated exceptional payload capabilities, carrying up to 14,000 pounds of bombs and missiles. On long-range missions, the aircraft could transport 8,750-pound bombs, along with electronic countermeasures gear and external fuel tanks. For shorter missions, this capacity increased to an impressive 16,750-pound bombs. The F-105's targeting capabilities evolved significantly throughout its service life. The AS-19 Thunderstick system provided both blind and visual weapons delivery options. This sophisticated setup incorporated the targeting system's effectiveness received validation during combat operations, with F-105Ds achieving 27.5 enemy fighter kills between 1966 and 1967. Most of these victories came through the precise application of the 20mm Vulcan cannon, while others resulted from Sidewinder missile engagements. Later variants, particularly the F-105G, incorporated specialized targeting equipment for the suppression of enemy air defense role. These modifications included advanced electronic warfare systems and specific armament for anti-radiation missions. The aircraft carried AGM-45 Shrike and AG-78 standard anti-radiation missiles, establishing new capabilities in radar installation neutralization. Combat experience drove continuous improvements in weapons integration. Engineers retrofitted many F-105D's radar, ultimedianskredid, untraden, askden, understick, gun bomb sights. These modifications improved weapons delivery accuracy and increased aircraft survivability in contested airspace. Engineering challenges. Despite its impressive capabilities, the F-105 Thunderchief faced significant engineering challenges throughout its operational life. These obstacles tested the ingenuity of maintenance crews and engineers alike, leading to continuous modifications and improvements. The F-105's status as the largest single-seat, single-engine combat aircraft of its time brought inherent challenges. Weighing approximately 50,000 pounds fully loaded, the aircraft's substantial mass affected various aspects of its performance. This weight created particular challenges during operations in Southeast Asia, where high ambient temperatures handicap takeoff performance, often requiring departures with reduced fuel loads. The heavy weight of the F-105 created additional stress on its landing gear components, which had to endure the strain of supporting and maneuvering the massive aircraft. This stress also translated into higher fuel consumption rates, as the Thunderchief required significant power to maintain its performance. In combat, its size and mass reduced maneuverability, making the aircraft less agile in dogfights and evasive maneuvers. During hot weather operations, the payload capacity was further restricted to account for the diminished thrust and increased lift requirements. These factors collectively posed operational challenges that demanded innovative solutions and careful planning. Compounding these issues, the Thunderchief's advanced and sophisticated systems introduced significant maintenance complexities. Early in its service life, the aircraft required an extraordinary 150 maintenance hours for every hour of flight time. This demanding maintenance schedule was driven by several factors, including frequent system failures in its electronics, the vulnerability of its hydraulic systems to combat damage, and engine cooling issues that increased the risk of fires. The avionics systems were particularly intricate, often requiring complex troubleshooting to address operational problems. The hot and humid climate of Southeast Asia further exacerbated these difficulties, especially affecting the reliability of the aircraft's electronics. Engineers responded to these challenges by implementing a series of enhancements. Ram air scoops were installed to improve afterburner cooling, reducing the risk of overheating. The hydraulic system received enhanced protective measures to minimize its vulnerability to damage. Upgraded electronic components were introduced to improve reliability, and additional armor plating was added to safeguard critical systems during combat. These efforts underscored the complexity of maintaining and operating the F-105 in demanding environments. Despite these challenges, the Thunderchief's robust design and continual engineering improvements allowed it to perform effectively as a premier strike aircraft during the Vietnam War, demonstrating its value as a powerful and resilient combat platform. While the F-105 excelled in straight-line speed, it faced several performance constraints. The aircraft's highly loaded wing, while excellent for speed and providing a smooth ride, proved less effective for sustained turns in dogfighting situations. This limitation became particularly evident when engaging with more maneuverable MiG fighters. The F-105D's early career was marked by numerous in-flight failures and maintenance issues. These problems persisted until 1967, despite multiple upgrade programs. The entire F-105 billion fleet faced temporary grounding in 1960 due to spare parts shortages. Combat operations revealed additional challenges. The loss rates in Southeast Asia reached concerning levels, with 382 aircraft lost, including 320 to enemy action. Of the 610 single-seat F-105Ds produced, 283 were shot down and 52 lost to operational accidents. The two-seat variants suffered similar attrition, with 37 shot down and 10 lost to operational causes out of 143 aircraft. The engineering team addressed these challenges through continuous improvements. The F-105D received updates, including enhanced ejection seats, radar homing and warning systems, additional armor protection, and reinforced hydraulic system components. These modifications improved the aircraft's combat survivability but added weight, creating a constant balance between protection and performance. The engineering challenges faced by the F-105 Thunderchief ultimately led to valuable lessons in aircraft design and combat survivability, influencing future aircraft development programs. Technical evolution. The technical evolution of the Republic F-105 Thunderchief represents a remarkable journey of continuous improvement driven by combat experience and advancing technology. From its initial conception to its final variants, each iteration brought significant enhancements to this formidable aircraft. The F-105's development began with Republic Aviation's internal project to replace the F-84F Thunderflash. The design team, led by Alexander Kartvali, evaluated 108 different configurations before finalizing the F-63 Fabex design. The progression of the F-105 through various models demonstrated a steady increase in sophistication and capability. The F-105D variant, with 610 units produced, introduced all-weather operational capability and incorporated advanced avionics systems. The F-105F, of which 143 units were built, served as a two-seat trainer while retaining full combat functionality, enabling both pilot training and operational deployment. A F-105G variant emerged as a specialized platform for the suppression of enemy air defense missions. Converted from the F-105F airframes, it was equipped with dedicated electronic warfare and anti-radar systems. The F-105D emerged as the most successful variant, featuring the APN-131 navigational radar and enhanced avionics systems. This version demonstrated remarkable versatility, carrying up to 15,430 pounds of conventional bombs during USF testing in June 1961, a payload 3 times heavier than World War II's 4-engine bombers. The Wild Weasel program marked a significant technical evolution in the F-105's capabilities. The modification process began with the F-105F variant and culminated in the sophisticated F-105G. Key modifications included the installation of specialized radar detection equipment, integration of AGSHRAE 5 Shrike anti-radiation missiles, addition of an ALK-105 electronic countermeasures in underside blisters, and redesigned wingtips for enhanced ROS system functionality. The F-105G represented the pinnacle of Wild Weasel development, incorporating advanced SEAD-specific avionics. Engineers fitted 30 aircraft with specially designed pylons to carry the AIM-78 standard anti-radiation missile, providing a significant improvement over the earlier Shrike missile. These aircraft proved crucial in suppressing enemy air defenses, often being the first to arrive and last to leave target areas. Combat experience in Southeast Asia drove continuous performance enhancements. Engineers implemented several critical improvements to address operational challenges. The F-105D received significant upgrades, including enhanced ejection seats for improved crew survival, radar homing and warning antenna installations, additional armor protection, and a reinforced hydraulic system with enhanced combat damage resistance. Environmental challenges in Southeast Asia prompted specific modifications. The high ambient temperatures and humidity affected electronics reliability, leading to the installation of ram air scoops to address afterburner cooling issues. The look-alike upgrades increased the aircraft's conventional weapons capacity from 4 to 16 750-pound bombs on underwing and fuselage centerline hardpoints. The F-105F underwent further evolution through various programs. The Commando Nail project modified several two-seat F-105Fs with R-14 radar and high-resolution radar scopes, enabling all-weather and night low-level strikes against high-priority targets. Combat Martin modifications added helicopters, Crick 128 VHF jammers to counter MiG attacks. Technical improvements extended to navigation systems, with 30 F-105Ds receiving an R-92 Lauren equipment in 1969 for enhanced navigation precision. These aircraft, known as Thunderstick VI, featured a distinctive long dorsal spine extending from the canopy to the tail fin. The evolution of the F-105's weapons systems kept pace with its other improvements. Initially designed for nuclear delivery, the aircraft adapted to conventional warfare through innovative modifications. The internal weapons bay received additional fuel tanks, while external mounting points expanded mission flexibility. Combat loads evolved to include various configurations, from multiple conventional bombs to specialized anti-radiation missiles. Wild Weasel variants demonstrated particular technical sophistication in electronic warfare capabilities. The F-105G incorporated advanced SEAD-specific avionics, including an upgraded raw system requiring wingtip redesign. To accommodate additional weapons, engineers permanently installed Westinghouse and ALK 105 electronic countermeasures in 2 long blisters on the fuselage underside. The Republic F-105 Thunderchief stands as a testament to 1950s aerospace engineering excellence. This remarkable aircraft pushed technological boundaries through its innovative area-ruled design, powerful J-75 engine integration, and sophisticated electronic suite. Engineers overcame significant challenges to create an aircraft capable of carrying massive payloads while maintaining supersonic performance. Over its service life, the F-105 underwent significant upgrades, notably in the Wild Weasel variants, which laid the groundwork for modern electronic warfare. The F-105 Thunderchief represents a pivotal moment in military aviation history, marking the transition from simple aircraft to sophisticated weapons systems. Its development overcame numerous technical hurdles, establishing new standards for fighter-bomber capabilities and proving that size need not compromise performance when paired with exceptional engineering. What do you think made the F-105 such an enduring and influential aircraft? Please share your opinion in the comment section. Like and subscribe if you like this video. Thanks for watching. See you in the next videos.